What exactly is FR3 fluid?
Well, FR3 Fluid is a renewable bio-based natural ester or vegetable oil. It has high flash and fire points. It quickly and thoroughly biodegrades within a matter of weeks. As far as I'm aware, there's never been a fire reported in a transformer that has been filled with FR3. Bad things about mineral oil is once it starts to burn, it's very difficult to put it out. The breakdown of cellulose produces water that leads to further breakdown. That's one of the reasons why in mineral oil filled transformers we see the water content slowly rising. That type of maintenance is far less required in transformers that are filled with FR3.
Can you push the KVA of a transformer with FR3?
Well, you can. There's a couple different things there when we talk about loading capacity.
Hey, Mac with Maddox here. Today we're here with a special guest, Bruce Forsyth with Cargill. Hey, Bruce, thanks for joining us today.
Thanks for having me.
Absolutely. So for those of you who don't know, Cargill is the manufacturer of FR3, which is a natural ester fluid used in transformers at Maddox and all over the world. And we get a ton of questions from our customers about what fluid type to use in their application, kind of what the differences are and why it matters. So today we're sitting down with Bruce here, one of the experts in FR3, to talk about what makes it different and when you should consider using it. So before we dive into FR3, Bruce, would you mind just kind of introducing yourself, give us your background a little bit and what you're doing right now?
Sure. Well, as Mac mentioned, my name is Bruce Forsyth. I'm the Director of Global Application Engineering for Cargill Bioindustrial. I'm an electrical engineer, not a chemist. A lot of the things we talk about have some chemistry involved, but we've got a great team of chemists at Cargill that I lean on for a lot of support. I've been in the transformer industry for about 38 years now. Most of that has been on the manufacturing side, designing transformers. And a couple of years ago, I joined Cargill, partly because I was just really interested in this change of these from mineral oil that has been used for many, many years to alternative liquids, specifically the natural esters is what I'm interested in. I've been involved, I mentioned, in transformer design, small transformers, distribution transformers up to large power, 500 MVA and 500 kV class. I started as a design engineer and I kind of worked my way up through the organizations at different places up to the point where I was involved in operations management. I worked for one of the major solid insulation manufacturers for several years, and now I've been with Cargill for a couple of years. I've had the opportunity to work with a lot of great people and learn over the years from different companies, different perspectives. And as I said, I've spent the biggest part of my career on the transformer side, so I really understand how the insulating liquid affects the design of transformers and the operation and service. I've also been involved in the IEEE Transformers Committee for over 30 years, had the opportunities to serve as chair of the Transformers Committee a few years ago, and meet a lot of great people that are involved in the IEEE and the Transformers Committee.
Awesome. Thank you, Bruce. So let's get into FR3 and just start with the basics. What exactly is FR3 fluid and what sets it apart from traditional mineral oil?
Okay, sure. Well, FR3 Fluid is a renewable bio-based natural ester or a vegetable oil. It's formulated from seed oils with a few additives to specifically make it suitable for use as an insulating liquid in electrical equipment, specifically transformers. It has high flash and fire points, which makes it qualify as a less flammable K-class liquid, which has a lot of good characteristics that we'll talk about, I think, in a little bit. It quickly and thoroughly biodegrades, so in the event that there is a bit of a spill, of course, that doesn't stop us from having an obligation to clean things up. But the good thing is that if there is a spill and there's some residual liquid around, it will biodegrade and be gone almost completely within a matter of weeks. It does not contain petroleum or halogens or silicones or corrosive sulfur. It's not a fossil fuel. It's a sustainable, renewable liquid. And standardized testing shows that it is non-toxic in acute aquatic and oral toxicity tests. Compared to mineral oil, of course, mineral oil is a petroleum-based fossil fuel, and while we probably never completely get away from fossil fuels, there's a big push around the world to try to minimize our dependency on fossil fuels, and using FR3 fluid is one of the ways of doing that. Mineral oil is much less friendly to the environment. It doesn't biodegrade the way natural esters do, and it's got a low fire point. And I think most of us have seen videos, unfortunately, of transformers that have caught on fire when something has gone wrong inside the transformer. And one of the bad things about mineral oil is once it starts to burn, it's very difficult to put it out. It feeds itself, and typically fire departments just kind of stand back and try to contain it so it doesn't go anywhere, but they just let it burn itself out. The mineral oil's got some characteristics that are not as desirable. It's worked very well in transformers for many years, but FR3 fluid provides some opportunities to go in a slightly different direction with some more desirable characteristics, particularly with regard to the environment.
That's great. Yeah, I kind of want to, that's a lot of great information. I want to get into each of those benefits there. I guess starting with the environmental impacts kind of aspect of FR3. So one thing we see a lot in transformer specifications is they want to see a fluid that's been, that's had some kind of a fish fry, like a baby fish study done on it, right? They want to make sure that if it's in a river, it's not going to kill the wildlife.
Correct.
What do those studies look like, and kind of what has FR3 been through in terms of studying environmental impact that way?
Yeah, those are the acute toxic, aquatic, and oral toxicity tests that I mentioned earlier. Basically, they're standardized tests where different organisms, fish and wildlife, and plants in some cases, are subjected to the liquid to see what impact it has, whether it goes away, whether it will kill fish, whether it won't. The tests that are used, I don't know the exact number, the OECD tests show that the FR3 is essentially non-toxic. So in the event that it does happen to spill and get into rivers and streams, the likelihood of it having a negative impact on wildlife or fish is minimal. In addition to the fact that it's biodegradable.
Tell me about the overloading characteristics of FR3. A lot of our customers are interested in FR3, especially solar customers or data center customers who tend to push the limits of the kVA, maybe run above capacity or at capacity 24/7 or with a weird loading cycle. What does that look like? Can you push the kVA of a transformer with FR3?
Well, you can. There's a couple different things there when we talk about loading capacity. In a transformer, in the insulation system, it's composed of both the solid insulation, which is usually cellulose-based, as well as the liquid. You can't separate them inside a transformer, inside a liquid-filled transformer. They work together. It's generally accepted that the cellulose is the weakest part of that insulation system. And when I say weak, I just mean it's going to age faster and reach what we'll call the end of life faster than the liquid will. Having said that, the electrical grade insulating papers that we use are very good electrically. But there's two main aging catalysts of cellulose, the paper. One is water. Water tends to cause the cellulose to break down. And second is temperature. We increase the temperature, we increase the aging rate. Both of these things, water and temperature. If you increase either of them, the aging rate increases. The temperature increase is typically through loading a transformer. And if the load increases, we're increasing the aging rate, which would decrease the life expectancy of that insulation. So we ask ourselves, is there something we can do about that? What if we were able to somehow remove the water from the system that would have the net result of reducing the aging rate with respect to the water content? And the answer is yes, that is very feasible with FR3 fluid. In a transformer, the water tends to want to distribute itself between the paper insulation and the liquid. And that's based on what's referred to as the relative saturation of those two quantities. Life likes to reach some sort of equilibrium, and in a transformer, the transformer will always strive to have the same relative saturation in the paper as there is in the liquid. FR3 fluid happens to have a very high water saturation limit, and so as far as the paper is concerned, the FR3 fluid always appears dry, and that has a tendency to cause the water to want to migrate out of the paper and into the FR3 fluid. Now, I should say that that process is the same with FR3 or mineral oil, the water will want to reach that equilibrium state. The difference is that with FR3, with natural esters and that vegetable oil molecule, there's a chemical reaction takes place. The water reacts with natural ester, and it's broken down and it's completely removed from the system. So the water has moved out of the paper into the liquid, and then it's broken down and removed. So it can't move back into the paper if conditions change. And the liquid, again, appears drier relative to the paper. And so there's a continuous desire, if you will, or incentive for the water to move out of the paper and into the FR3 fluid. That continuous drying process keeps the paper dry, and through that process, we've reduced the aging rate of the paper. And that allows the opportunity to either extend the life of the transformer or, going back to that load, allow the load to increase a little bit and raise the temperatures and maintain the same, what I'll call the normal expected life of a transformer. So it's a tremendous opportunity. There's two things there. When we remove that, remove the water from the system, you can either extend the life of the transformer or increase the load. Now, specifically, you talked about in solar applications where we know that the load on the transformer is cyclical. There's times of the day when there's a high load on the transformer, and then the sun goes down and very low load. Strictly speaking, if you're just using mineral oil, you'd probably need to design the transformer for that peak load. If FR3 is used, that's not necessarily the case because we can take advantage of the overload capabilities, the higher temperature capabilities of natural ester. FR3 is considered a high temperature insulating liquid as opposed to mineral oil, which is not. And so you can allow the transformer to temporarily operate at higher loads and get a little bit warmer. And then when the temperature drops, it's back down to some other temperature. So there's an opportunity there to do, we sometimes refer to that as a sustainable peak load for a transformer that's designed with FR3 for a particular rating. We know that we can allow it to operate above that nominal nameplate rating without having a dramatic negative impact on the life expectancy of the transformer.
Mm-hmm. Yeah, I think it was S.D. Myers that put it really succinctly that the transformer's lifespan is the health of the cellulose paper insulation.
Absolutely.
Right. So it seems like kind of one component, maybe, to a layman, it seems like, maybe simple, but the truth is transformers don't break down like other machines because other machines have moving parts. There's mechanical wear. With transformers, the life expectancy, as long as there's no, issues with any ancillary components, really is in the insulation paper. So preserving the health of the insulation paper is extremely impactful on transformer longevity.
Absolutely. And when we talk about the life expectancy of a transformer, a normal life expectancy, we're usually talking about something in the order of 20 years.
Right.
And that's when the transformer is operated at full load continuously for those 20 years. And we know that most transformers don't operate at full load, and that they're not operating at full load, they're running a little bit cooler. And so the aging rate slows down. And that's why we hear about so many transformers that last 50, 60 years before they reach what we'll call the end of life. And that end of life, as you mentioned, is typically the point where the paper insulation that's in the transformer will somehow break down and no longer protect the either dielectrically is ultimately why transformers will normally fail. The paper will break down and no longer provide the dielectric insulating values that it normally should have, and the transformer will fail.
Now, I thought I had read somewhere that the acidity, like the acid level in the transformer fluid, can actually contribute to the breakdown of the insulating paper, and FR3 is less acidic than mineral oil, or something like that. Is that a
similar, something like that? I mentioned that that water that I didn't call it a hydrolysis reaction, but when I mentioned that the water will react with the natural ester, that's a hydrolysis reaction, and one of the byproducts of that is acids. But when we hear about acids and acid levels in transformers, we always say that's a bad thing, and it's not a great thing. But the acids produced by mineral oil, which they are produced, there's also as the transformer operates, acids are produced. The acids produced by mineral oil are more aggressive against the components inside the transformer. They form sludge and things that will have a negative impact on the transformer operation. The acids that are formed through the hydrolysis reaction in natural esters are much less aggressive on the insulating components. They don't attack the metal the way acids in mineral oil will. And there is some discussion, there is literature that suggests there's a process called transesterification where some of those acids can actually react with the paper insulation and kind of form an additional insulating value on that paper. But there's other studies that's not well, the conditions for that to happen are very specific, and it's not well understood whether that's a common thing to happen in transformers. Theoretically, it's possible, but I haven't seen papers that suggest that it's a very common thing to have happen. But the good thing is, as I said, that the acids that are produced in natural esters are not nearly as aggressive against the components of the transformer. They don't form sludge. They will increase the acid number, and they will affect over time the viscosity of the liquid, but they're not as aggressive to the components inside the transformers as the acids produced by mineral oil.
Now, one thing we see on occasion when it comes to testing, if a client has a NETA testing firm doing some routine testing or startup testing, including maybe pulling a DGA, there are some kind of differences in how you read test results depending on if you're testing an oil-filled transformer or FR3. And if you don't know what oil is in the transformer, you could get a false positive on this or that
Absolutely.
test. Can you tell me about that? I don't know much about
Sure.
that. I'd like to learn.
So the fundament, when a transformer is operating, there's various temperatures inside the transformer. Typically, we look at the top oil temperature gauge and we see it's operating at 90 degrees Celsius or something like that, whatever the normal, whatever the temperature is at the time. But that's the bulk oil temperature. Within the transformer, for many different reasons, the distribution of electric fields and things like that, there can be much higher localized temperatures. Those high temperatures will have a tendency to provide the energy, sufficient energy to break down the oil molecules and sometimes the paper molecules as well. That happens with both mineral oil and with natural esters. Mm-hmm. The gases that are produced during that process, whether it's mineral oil or natural esters, that the gases themselves are typically the same types of gases. We see hydrogen, ethane, methane, ethylene. In bad cases, acetylene. Normally, when we see acetylene, we say something's gone wrong. Right. It takes a lot of energy for acetylene. So the gases that we look at are the same, but the relative concentration, the ratios of the gases that are produced at different temperatures changes based on the liquid that's in the transformers. So as you mentioned, when you pull an oil sample and are looking at these gases and you look at the relative concentrations of the different gases, it's very important to know what liquid you're dealing with, because if you try to apply the normal ratios of gases for mineral oil when it's actually natural ester, you could misdiagnose an issue. And similarly, if it's FR3 and you're or if you're trying to use FR3 guidelines for mineral oil, you just don't want to do that. So it's very, very important to understand what the liquid is inside the transformer. This is going to be an issue, I think, that comes more and more common in the years moving forward, mm-hmm. as the use of natural esters becomes more and more common.
Mm-hmm. So basically, the way that a hydrocarbon fluid responds to issues inside a transformer, overheating or arcing or whatever, basically it just responds chemically different than a natural ester. So it's going to have a different profile. If the same thing happens to two separate transformers, they got two different fluids, the chemical profile is going to change just in different ways.
Yes.
Okay.
Yes.
Right. Another question we get a lot about transformers and fluid is kind of startup procedures, like how those change between fluids. Can you talk about that? Is there any difference?
The basic start, so you're talking about cold temperature startup procedures primarily.
Right.
With transformers, they're normally designed to operate from temperatures from about minus 20 degrees Celsius up to about plus 40 degrees Celsius. I think the IEC standards is minus 25 degrees Celsius for low temperature. And so any transformer, that's going to be subjected to a cold start at minus 20 or below should go through a cold start procedure. The purpose for this, if you just suddenly put load on a transformer, you can have a couple of things happen. First of all, it'll sort of thermally shock the insulating system. You can have bubble formation because of the rapid change in temperatures, and you don't want to do that. So the bottom line is any transformer at cold temperature should go through a cold start procedure to slowly ramp up the temperatures. Now, the big difference between mineral oil and FR3 is related to a thing called pour point. When FR3 gets cold, it starts to crystallize. It doesn't freeze like water, but it starts to crystallize. And even though the crystals, oil with crystals still maintains very good dielectric properties, it becomes more and more dense. It won't flow as well. Obviously, if it's crystallized, the viscosity goes up. And there comes a point where we reach what I call the pour point, where the crystallization is so dense that if you were, for instance, to take a vial of the liquid and turn it on its side, the crystals are so dense that they don't flow anymore. So, and that will happen. The pour point of FR3 is around minus 21 degrees Celsius. So if a transformer is been subjected to minus 21 degrees Celsius or lower for an extended period of time, the liquid inside the transformer could be fully crystallized. Now, I could spend a lot of time talking about this, but I'll just say that just because the ambient temperature dips to minus 21 degrees Celsius doesn't mean that everything in that transformer is immediately crystallizing. There's a huge thermal inertia inside a transformer, particularly if it's in operation. There's enough heat being generated that even though the ambient is minus 20 or minus 30 degrees, the temperatures inside that transformer are going to be much higher than that, and the fluid is flowing. But in a situation where a new transformer has been delivered, or for some reason the transformer has been de-energized for an extended period of time, it's possible that the liquid could be in this crystallized state in an FR3 filled transformer. When that happens, a couple things. Mechanical devices shouldn't be operated. That means load break switches or de-energized tap changers or even pumps because the fluid isn't flowing the way it was. Now, I say they shouldn't be operated. They shouldn't be operated unless it's known that they've been designed to operate in fully crystallized liquid, which is not that common right now. It is important then that the transformer go through a cold start procedure. And again, the fundamental cold start procedure is the same for even for mineral oil transformers. It typically involves energizing the transformer with no load, if possible, holding it that way for several hours. The no load losses are usually enough to raise the oil temperature, I'll say roughly 15 degrees or something like that. Don't hold me to that. That number could go up and down depending on the specific design. But the point is there is a fair bit of energy being heat being put into the system that will raise the temperature of the oil. And then the next part of the cold start procedure is to slowly add load, typically in about 25% increments over several hours. Hold 25% load for a couple of hours and then increase it another 25%. And that way you're slowly raising the temperature of everything. And as in the transformer, the heat is coming from the core and the coil assembly inside the tank. And it will migrate out and slowly melt. I use that word melt, but move that liquid from its crystal form back into the liquid form where it's flowing. The good thing about FR3, as I said, even in its crystal form, it maintains its dielectric strength, which is something I'll just mention is a huge benefit compared to mineral oil. At cold temperatures, mineral oil becomes very weak dielectrically. It has to do with the saturation limit, the water saturation limit of of mineral oil at cold temperatures like minus 20 degrees is something like 8 parts per million. And that's not an uncommon amount of water to have dissolved in a transformer. Mm-hmm. And if the insulating liquid is highly saturated, that means that there's 8 parts per million water in that insulation system with mineral oil. Then the oil is going to be 100% saturated, and the breakdown voltage is very low. So the risk of a dielectric breakdown or cold start with a mineral oil filled transformer is much higher than with FR3, because the FR3, as I said, maintains its dielectric strength. But it is important to go through that procedure, make sure the liquid is flowing before any mechanical devices are operated, and preferably be able to get know that the oil temperature is up. A safe number is minus 10 degrees Celsius. At minus 10 degrees Celsius, everything should be flowing, and there shouldn't be any concerns about operating mechanical devices.
And on the so on the cold startup, basically what you're describing is the same cold startup procedure you would want to perform. If you're energizing a transformer in North Dakota in the middle of winter, you're going to want to go through that startup procedure, no matter the fluid. The only thing to keep in mind is maybe the mechanical devices with the crystallization, but you really wouldn't want to be operating those devices during a cold startup procedure anyway. So
I would agree with that. Yeah.
Yeah. So, if you've got the miserable job of energizing a transformer in the middle of Alaska in the winter, then God bless you.
Yeah. And it will happen. It can happen. It's just, and this goes to, again, what I've said, it's very important to understand the liquid that's inside the transformer. We talked about DGA analysis, whether it's DGA analysis or a cold start procedure. It's important to understand what liquid is inside the transformer and to follow the proper procedures for that specific liquid.
Okay, so Bruce, what's the difference between the flashpoint in FR3 and traditional transformer oil? Kind of why does that matter?
Okay, sure. So the flashpoint, there's two things we talk about with regard to that are related. One is flashpoint and one is firepoint. They're somewhat related. The flashpoint is the lowest temperature at which a liquid can produce enough flammable vapor to ignite momentarily when exposed to a source of ignition. The test is simply that. There's a cup, vapors will form on top. At some point, a flame is introduced, and if it flashes, if there's enough volatile vapor there, it will flash. That's the flash point. The step beyond that is the fire point, and that's the same basic procedure, except when it flashes, it actually sustains a flame for, I think it's 5 seconds or something like that. The flash point for mineral oil is about 140 degrees Celsius. The flash point for FR3 is around 320 degrees Celsius. More importantly, I think, is that fire point. The fire point for mineral oil is around 160 degrees Celsius, and for FR3, it's around 360 degrees Celsius. So anytime if the fire point is above 300 degrees Celsius, the liquid is considered a K-class liquid, a less flammable liquid, and that's where FR3 falls. Most of us have seen pictures of transformers that have caught fire. When there's faults inside a transformer, there can be tremendous temperatures built up, and that can be enough to ignite the liquid. If oxygen is allowed to get into the system, that's usually what happens. There's some sort of a problem. There's a bushing breaks, oxygen gets in, you've got oxygen, you've got an ignition source, and you've got the components that can burn. And when the transformer starts burning with mineral oil, it just keeps burning until the oil is gone. With natural esters, the fire point is so much higher that the risk of a fire is significantly reduced. As far as I'm aware, there's never been a fire reported with in a transformer that has been filled with FR3. In any event, what we do know is it's much the risk is much lower. And what also one of the benefits of FR3, just the nature of the liquid. When it does burn for some reason, if it were to start burning because of an arc that was burning it, if you take away the ignition source, typically the fire will go away, which is unlike mineral oil. Mineral oil, once it starts burning, it generates enough heat that it just feeds itself and it will continue to burn. So these are very important characteristics, particularly for transformers that might be considered for indoor applications. Typically, you would not put a transformer filled with mineral oil in indoors because the risk of fire and the horrible things that could happen if it was indoors with people and the structure, the risk of a fire would just be too high. But when using a less flammable liquid, it's frequently allowed to be used indoors specifically because it's a less flammable liquid. FM Global has some guidelines for that with regard to the application of less flammable liquids. And so that's a huge benefit of FR3 over mineral oil, and probably the primary reason people will select FR3 versus mineral oil is because of that significantly decreased risk of fire.
Mm-hmm. Now, we used to see a lot of old General Electric or Ferranti Packard indoor subs built with silicone, which is also K-class. I haven't seen silicone put in a transformer. Probably the newest nameplate I've seen with silicone was maybe the 90s. Can you tell us a little bit more about kind of the phasing out of silicone and FR3's replacement of it?
Well, what I can tell you is one of the good things with mineral oil, if a person wanted to do a retrofill, mineral oil and FR3 are fully miscible, and it's possible to take the mineral oil out, replace it with FR3. There's a flushing process that one would go through to just clean out as much of that mineral oil as possible. But the net result is you could end up with a transformer with FR3 that has no more than about 5% mineral oil in it, and it will perform as expected. Silicone's a little different. Silicone and FR3 are not miscible, and so there's no opportunities to do retrofills with transformers filled with silicone. Silicone is a little bit more difficult to work with, and as you suggested, some people just try to stay away from it if they possibly can for different reasons. I'm not saying that there's not a good use for it, but one of the challenges we get questions on is with silicone-filled transformers. Can they be retrofilled with FR3? The answer is typically no, because we just can't. It's not miscible, so if you drained it and put the liquid in, you'd have pockets of different fluids, and that would create a dielectric weakness in the transformer. So we don't do retrofills on silicone-filled transformers.
Yeah, I've seen like vials where you put mix the different oils and you can see how they mix. In silicone, it's like oil and vinegar almost.
Right.
So my understanding is basically when if you've got them close together like that in the core and coils, it kind of creates potentially a space for an arc to travel along. It just doesn't
changes,
mix, right?
Yeah, it changes the dielectric, the field strength within the transformer. When we energize a transformer, I think everybody's. I'll use a magnet example. If you take a bar magnet and sprinkle iron filings, you see the magnetic field that it creates. Inside a transformer, once it's energized, there's similar sort of electric fields produced. When you have different mediums like that, it changes the distribution of that electric field. And if you have two different liquids that aren't miscible, you really don't. It's almost impossible for a design engineer to predict what those stresses would be in different places. So it really is just not something anybody would want to do. I don't know anybody that would recommend just trying to operate a transformer with a mixture of silicone and either FR3 or mineral oil, for that matter. It isn't a good idea.
Yeah. Could you run it through a process of rinsing and drying and rinsing and drying to get it out? Obviously, you don't want to just dump it and drain it and dump it, do it like that. But is there any kind of really involved process that would make that process okay? So
again, I'll go back to the mineral oil and the FR3 process. When we do a retrofill, there's a couple of different ways of doing it. If you're in a factory and you have access to a vapor phase process, for instance, it's great because you can take the drain the oil out, put the core and coil assembly in the vapor phase oven and dry it out and really get rid of everything that's in there. But there's always going to be some residual material in there. And then when you fill it with the FR3 will impregnate into the transformer and it will behave properly. In the field, it's more difficult to do that. We don't normally have the vapor phase processes and retrofilling, which has been done many times. There's probably 50 or 60,000 transformers that have been retrofilled. We
From
go
mineral
through
oil to
normally
FR3.
mineral oil to FR3.
Yeah, we do it all the time.
We go through a flushing process, and an important thing to recognize is that solid insulation that has soaked up that mineral oil. Even after you drain it and let it sit for a little while, there's still some residual mineral oil in that solid insulation. And when you fill it with FR3, eventually it will mix and reach some degree of equilibrium. But initially, there's going to be a higher concentration of mineral oil compared to FR3. In fact, that has been observed with the testing procedures after you
shows
do
up in the DGA, right?
Well, it'll show up in insulation resistance, possibly the dissipation factor, because those are all capacitance based. And as over time, as the FR3 fully impregnates into the solid insulation and reaches equilibrium, those numbers will stabilize. But if you take make those measurements immediately after retrofilling, you'll find that over the next weeks and possibly months, depending on the size of the transformer and the amount of paper insulation, those values may change a little bit until they stabilize. And that's just because of the time it would take to mix. With silicone, they never really mix. So to your question of can you take a silicone filled transformer and put it through a thorough drying process? I suppose theoretically you could. I'm not really aware personally of people doing that. Typically, we don't recommend mixing the silicone with FR3 in particular, because there will always be some residual silicone in there, and there's a risk then of having a performance problem that's uncontrollable.
All right, so let's talk about the cost difference, because we basically always recommend FR3 in any application that we can for all of the benefits. The only time we might not is if it's a real cost-conscious customer and they're really pinching pennies, and maybe they're putting the transformer into a project that they're going to sell within a year anyway. So they really, they don't really care about the longevity of the transformer, necessarily. But can you kind of walk us through that? I mean, when you hear talk about costs, like what are the benefits? What's the payoff?
Sure. So that's a great question, because you always have to look at the motivation. Why would somebody use FR3 versus mineral oil? The fact is FR3 typically does cost a little bit more than mineral oil. And so if everything's just cost driven, the mineral oil design may end up coming up with a lower cost. But if the owner or the buyer says, I need that high fire point, fire safety is important to me, or biodegradability is important to me, or this life extension or ability to overload the transformer is important to me, then that becomes a part of the specification that can push somebody towards using FR3. Another place where this becomes very important is in the design of substations. Because of the higher fire point, the K-class liquid, less flammable liquid, many fire regulations, depending on the jurisdiction, will allow transformers to be placed closer to one another or closer to buildings. And firewalls can sometimes be eliminated, and even the deluge systems can be simplified or eliminated simply because there's a less flammable liquid inside that transformer as opposed to mineral oil. And that simplifies the design of the substation. Even the spill containment can be simplified. In many cases with mineral oil spill containment, there's the primary spill containment if oil's coming out of the transformer. But for fire reasons, you don't want the transformer sitting in a pool of flammable mineral oil.
Right.
Typically, there's also a secondary system where the oil would be drained away and contained away from a potential fire. With the transformers filled with less flammable liquids like FR3, that secondary containment isn't necessarily required. So it simplifies the design of the substation. There are some utilities. In fact, I visited one in Brazil recently that takes advantage of this, and they have significantly reduced the cost of designing substations by taking advantage of this, the high firepoint of FR3 in
Oh, wow.
particular, to reduce the cost of their substations. The numbers that they presented to me is the cost of designing a substation today with FR3, with everything put closer together, is on the order of 50% of what it would cost with mineral
Wow.
oil.
Wow.
So if the initial cost of the liquid is a little bit higher,
Hmm.
it by far outweighed by the cost savings for the entire substation.
Hmm.
In addition, this life extending characteristics, by taking the water out, we can extend the life expectancy of a transformer.
Hmm.
Many owners of transformers will now amortize a transformer instead of over 30 years. Now they'll amortize it over 40 years. And that can
Hmm.
have in the cash flow calculation, in the net present value
Yeah.
calculations, that can have a direct impact on the overall value of the transformer.
Yeah.
I didn't really talk about maintenance during the life of a transformer,
Let's talk about
but
it.
we talked a little bit about the acids production inside a transformer. I talked about sludge formation.
Hmm.
Um, I didn't really mention. I mentioned water is an aging catalyst of cellulose, and in a twist, if you will, when cellulose breaks down, that's what we call aging. It's a chemical reaction, really, but the
Hmm.
cellulose molecules, the polymers, will break down. When they break down, they produce water.
Hmm.
So it's what we call an autocatalytic reaction. The breakdown of cellulose produces water that leads to further breakdown. And so that's one of the reasons why periodically in mineral oil filled transformers, we see the water content slowly rising, despite, the owner's best maintenance practices. Water content will rise, and periodically companies will come in, process that oil to dehydrate, to take the water out. They'll filter the oil to take some of that sludge out. They'll probably degasify the oil and then put it back into the transformer and get a new baseline and move on. That type of maintenance is far less required in transformers that are filled with FR3 because the water doesn't form. The water is taken out is removed from the system by the FR3 itself.
Hmm.
The Any acids that are formed don't form sludge. Over the life of a transformer, the maintenance costs are typically lower. So when you look at the
Hmm.
full life cycle of a transformer, even though the initial cost of that FR3 might be a little bit higher than mineral oil, over the life of the transformer, there's a savings. Now, you
Hmm.
also mentioned things like, if you have one company that builds a substation, does things, and then they're just going to sell it, sometimes that doesn't always get realized by the ultimate owner of the transformer, and that can be a challenge. But when we look at
Hmm.
using FR3, we look at, again, the three main reasons, the motivators, if you will. One is the fire safety, second is the environmental issues, and the third is the ability to either extend the life of the transformer or take advantage of the opportunity to increase load on the same footprint, basically increase the power density.
Hmm.
And that is, I have found that is more important to people than extending the life of the transformer. They're more
Hmm.
interested in, just because space is always a constraint, trying to get as
Hmm.
much power through that transformer as possible.
Yeah, the real estate, the physical space, obviously, is a huge cost savings.
Yeah.
But also, I can imagine, especially for a big industrial end user, if you can amortize that piece of equipment, if you're talking about a big sub
Yes.
that's $1 or $2 million, it's powering your whole operation, and you can double the amortization timetable, that
Yeah.
is potentially huge. Is there anything else we should know about FR3?
Yes. In solar applications, in some of the renewable applications with both solar farms and wind farms, when transformers are connected somehow to inverters or converters, those devices tend to introduce harmonics into transformers. And while we've learned a lot over the last many years as renewable sources have become more popular, but in the early days, a lot of times the transformers associated with those devices were, I'll say, followed just a typical distribution transformer design. And unfortunately, this harmonic load creates within transformers what we refer to as harmonically induced partial discharge. It basically, the sinusoid that's being provided to the transformer has a lot of noise in it. And what we have found is a lot of those transformers produce a lot of hydrogen. When there's partial discharge in transformers, one of the typical gases that's produced is hydrogen. And hydrogen can be a very dangerous gas. And the partial discharge inception voltage of FR3 is slightly higher, 10 to 15% higher than mineral oil, based on a lot of different tests. And there has been some very good success cases in situations where transformers connected to inverters have been producing high levels of hydrogen, and the oil has been retrofilled, the mineral oil has been removed, and FR3 has been introduced to the transformer, and the hydrogen generation is significantly reduced back to what would be considered normal levels. Wow. Now, that doesn't mean we've changed the design. The electrical stresses are still the same inside that transformer, but it just turns out that the FR3 is a little bit stronger electrically, and so the partial discharge doesn't take place, so we have a safer situation. Today, new transformers have, with that knowledge of those issues, I think transformers in those applications are being designed a little differently so that they can withstand that harmonic load better. But there are a lot of transformers that are out in the field in these applications that are generating hydrogen. So retrofilling them with FR3 has been proven to be a successful and reliable way of reducing those dangerous levels of hydrogen.
Yeah, that's great to know, because we do quite a few repairs on wind and solar transformers where there are elevated levels of hydrogen, and oftentimes their directive to us is just replace the oil or clean up the process the oil, send it back to us. We know it's an issue, we're not changing the design, just we'll keep running for another 5 years. So that could be a huge advantage to them if we actually recommend they switch to FR3. That could actually
absolutely
fix the issue going forward.
That has been a proven success in many different applications. It's not a guarantee, because if the harmonics are high enough, it may even exceed the strength of the FR3. But we've had there's numerous success stories where that has bought the owner a little bit of time. To your point, they no longer have that specific issue that they have to worry about.
Yeah, because like you said, you call it harmonically induced partial discharge.
Yes.
Right. So that's because of the way the transformer is designed. FR3 doesn't fix the transformer design. It just withstands the negative effects of that discharge, right?
Correct. Because the inverters create, and the converters create what I'll call a pseudo sinusoid. It's not a smooth sinusoid. It's actually a whole bunch of little square waves. Typically.
Yeah, it's like stair steps, right?
Yeah, there's technology to smooth that out as much as possible. Yeah. And so some are much smoother than others, but still, any distortion in that sinusoid will tend to increase the harmonics that are introduced in a transformer. And harmonics, it's superimposed on the sinusoid, so you get a really noisy looking sinusoidal signal. And those harmonics primarily affect thermal issues inside the transformer. All the metal components and things can get a lot hotter than expected. And that can, when there's that much heat inside the transformer, it starts breaking things down and producing these gases. And so
if you're going to DC, from DC to AC, whether it's solar or wind, or maybe even big data center loads that the load is actually very DC heavy, FR3 is good because it can help withstand the heat created by that messy signal, right? Okay.
Correct.
Yeah, so there's two benefits there. There's the hydrogen thing, and then also just dealing with that heat without the oil actually breaking down.
Correct. That's correct. That's one of the better of the benefits I mentioned about FR3 is it is a high temperature insulating liquid. So it can operate at higher temperatures. Typically, when mineral oil filled transformers are limited, the oil rise, top oil rise is limited to 65 degrees Celsius. The reality is that's because if you start going much higher than that, the oil itself can start to degrade. The mineral oil will start to degrade. But FR3 natural esters can operate at significantly higher temperatures without the impact. So we can really take advantage of that in certain designs. I didn't even mention the high temperature designs. There's also opportunities when designing a transformer if the end user will allow the transformer to operate above this traditional 65 degree rise limit. Then the design engineer can take full advantage of the thermal strength of FR3 and use the right insulating materials to allow the transformer to normally on a day-to-day basis operate at a higher temperature and maintain the same expected life as a mineral oil filled transformer, but this higher temperature transformer will be much smaller.
Yeah, that's great. I know I sold some transformers going to Death Valley a couple of years back, and we designed them to have 55, 65 degree rise and FR3 because we knew, even though loading was relatively normal, that higher ambient temperature is not going to treat the oil or the transformer very well at all.
Right.
So let me ask you one quick question about, this is more of a transformer design question, but you said something about, transformer manufacturers are getting better at designing transformers that can tolerate those harmonics better with DC to AC conversions. Is part of that K factor?
So knowing the K factor, meaning the harmonic content, that's important. When the transformer is being designed, being able to provide the level of harmonics that are expected is really important. To provide that with the transformer designers so that they can make the right decisions. It's also some shielding within the transformer that they can put shields in that will help mitigate the impact of the harmonics in the system. So to your point, yes, K factor is a part of it when you're talking about the K factor associated with the different harmonic content. That's always very important for the transformer designers to know, because otherwise they will assume default levels that may not represent the conditions the transformer will see in service. So if those things are known, they should be provided to the transformer designer in advance.
Bruce, thank you so much for being with us today. Any last words before we let you go?
No, thank you for having me. I would just like to say thank you for doing this. I think this type of training sessions are great for the industry. There's a lot of people that can learn from these things, and it's really good that there's people like you, companies like you, that are willing to spend the time out of your day to try to share some information that can make the whole industry better. So thank you for what you do.
Thank you, Bruce. Talk to you later.
Okay, bye now.